Okay, so all right, so Mythbusters TV show, they wanted to see if yawning is contagious. They select 50 people to participate. Each participant's told to sit in a small room, monitored for several minutes, and before they enter the room, some of the people see a person yawn, and they call that the seed yawn. Other people do not. They call that the control, and the Mythbusters team records who yawns and who does not yawn. And the summary data is this. So they had 50 people total, and they don't give the actual numbers, but based on what they said, I kind of worked backwards to figure out these numbers, right? They said 29% of the seed yawn group yawned, and 25% in the other group didn't, and that basically 2 out of 3 got a seed yawn, and every third was a control, okay? So anyway, something to keep in mind, the sample of people was not randomly selected, but the treatments are randomly assigned, okay? So technically the assignment is what we call systematic, but I think it's reasonable to think that the order of persons is random, right? So if, if the order of persons could have been in a different arrangement, and then they would have had different assignment of treatments, right? Okay, so anyway, for the seed yawn group, 10 people yawned out of 34. So our observed proportion would be p hat seed. 10 divided by 34 is 0.294. Okay, and then for the control group, 4 out of 16 yawned. So 4 out of 16 is 25%. Okay, and then the Mythbusters, their conclusion is there's little doubt it does seem to be contagious. So what do you guys think? This difference of 4%, are you guys convinced? Yawning is contagious? Maybe? Maybe not? Okay. A lot of you are shaking your heads. All right, so we're going to do set this up as a proportion hypothesis test, right? 2 proportion hypothesis test, just like the Z proportion hypothesis test, except we're not going to use the normal distribution. We're not going to use the central limit theorem here, okay? We're going to do a randomization test. So here, we do P seed. This is going to be the probability of yawning given the seed group. P control will be probability of yawning given the control group. Here, the null hypothesis is that yawning is not contagious, or symbolically, that means the probability seed, P seed minus P control, is equal to 0. The alternative is that yawning is contagious, meaning that if you see someone else yawn, getting a seed yawn makes it more likely for the person to yawn. So we're going to say P seed minus P control. In this case, we are expecting those who got the seed group more likely to yawn. So we're going to say P seed minus P control is greater than 0, that the difference is greater than 0, right? Okay, and our observed data is P hat seed, that's what we actually observed, minus P hat control. That difference is around 4.4%, 0.044, okay? P hat seed is 10 out of 34 minus P hat control, which is 4/16 or 1/4. That difference is around 0.044. And the question is this difference of 0.044, is that statistically significant, right? If the null hypothesis were true, we would expect a difference of 0. We didn't get a difference of 0, we got a difference of 0.044. And so is that difference statistically significant? That's what we want to know. Okay? And so in this case, kind of just to further explore the null hypothesis, right? If the null hypothesis were true, it means this treatment, getting a seed yawn versus not getting a seed yawn, being in the control group, has nothing to do with the actual person actually yawning. Okay, that's what the null hypothesis is stating. It's saying that getting the seed yawn doesn't make you more likely to yawn. It has no effect, right? And that, this difference of 4%, 0.044, that could have been just because of randomness, right? Another way to think of this is to say that, in our sample of 50 people, 14 of them were just destined to yawn. They were going to yawn no matter what, okay? And the fact that 29% in one group yawned and 25% in the other group yawned could be just a result of randomness, right? Of the random assignment. And that randomness alone could produce this difference of 0.044, right? That's what we want to know, okay? And so to answer that question, we need to figure out the p-value. The p-value is the probability of observing our data or something more extreme if the null hypothesis were true, right? So if the null hypothesis were true, we would expect to see a difference of 0. We observed a difference of 0.044, right? So the question, the p-value is, if we assume that the two proportions have the same, if the two populations have the same proportion of yawners, then what's the probability that random assignment could produce this difference of 0.044 or something more extreme? That's what we want to get after. All right, and so this is when we are going to do the randomization test, okay? So the randomization test does not rely on the central limit theorem, okay? And what it will do is it simulates this random assignment process, the random assignment of the treatments that could happen if the null hypothesis were true, right? So this is what we're going to do. Simulate the random assignment treatments that could happen while the null hypothesis is true. So we are going to set it up so that we're going to have 50 people, and 14 of them, we're going to say these 14 people are destined to yawn, okay? And then I take my 50 people, I shuffle them, and I'm going to just randomly put 34 in this group and 16 in this group, and I'm going to see, okay, in this group of 34, what proportion yawned, okay? In this group of 16, what proportion yawned, okay? And then I calculate those proportions and I get the difference between them, okay? And because I did the random, the mixing up, okay, we did the random assignment ourselves, we know that who ended up in this group and who ended up in this group has nothing to do with the seed yawn or anything. It's just, we just randomly put some people over here and randomly put some people in the other group. So we know there's, so we know that the proportion difference that we observe is just a result of randomness, okay? And so we want to know how often does this random proportional difference end up being 0.044, right? So we're going to do this like thousands of times, okay? Every time we do it, we record the difference between the two group proportions, and that'll give us basically a sampling distribution. And what we're going to do is we're going to find the proportion of times that the random assignment process produces a difference of 0.044 or something greater, okay? Because that's what we observed. We want to know how, what's the probability of getting 0.044 or something greater, right? Okay, this time, right, so every time you do something in statistics, we're making assumptions. It is impossible to do statistics without making some assumptions, and you need to be aware of the assumptions you're making, right? So because we knew the assumptions we were making when doing a z proportion test, we know that it is not appropriate to do a z proportion test in this case, okay? And here we're going to do a randomization test, okay? So the assumption in the randomization test is exchangeability, all right? So exchangeability is this idea that when the null hypothesis is true, all possible permutations of the data are equally likely, and that any permutation of the data is exchangeable with another permutation of the data if the null hypothesis were true, okay? So that's like weird to say, but what does that mean, okay? Basically, it means that if you have an experiment where there was random assignment of treatments, this premise of exchangeability applies, okay? So for the Mythbusters, the people order of those 50 people could have been something different, okay? And then we would have had different assignment of treatments, right? Because so if you think of a random experiment, right, you do some kind of controlled experiment, and I don't know, you shuffle them up and you say these people are going to get the experimental treatment, these people are going to be control. Someone else could have shuffled them up and the assignments could have been different as well, right? And is any one of those random assignments more valid or less valid than the other? And the answer is no, right? So any random set of random assignments are exchangeable, okay? If you think of an observational study, in an observational study, it is not, the treatments or the conditions or variables are not exchangeable, right? So maybe you're doing an observational study and you want to see is, I don't know, some health-related outcome related to whether, I don't know, people brush their teeth or not or something, right? Like the frequency of brushing their teeth. And so you survey people and you measure these health outcomes, and then you ask them, do you brush your teeth or not? Or how often do you brush your teeth? And the answers that people give, those are not exchangeable. You cannot say, well, this person brushes his or her teeth, twice a day, every day, and this person, brushes their teeth, less often than that, and the brushing habits are probably related to other things that could be related to health outcomes, right? Like hygiene preferences and stuff like that. That's not exchangeable. We cannot just say that, on another day, we would have gotten different responses, okay? When you do random assignment of treatments, it is reasonable to say, had I done the random assignment on another day, I could have ended up with totally different random assignments. That's a reasonable thing to say, okay? But people's preferences regarding, survey information in an observational study, those are not going to be random exchange. Those are not exchangeable, okay? So if you did not do random assignment as part of the data gathering process, don't use a randomization test. That's kind of your key idea here. Okay, we've got other methods. On Wednesday, we'll look at Bootstrap, and that applies more to this random sample stuff. Okay, but anyway, I gotta hurry along. So that's what we have. Okay, so here's my setting up of the data. Yawning, it's a vector of 50. It's a logical vector of length 50. I said repeat true 10 times, repeat false 24 times, repeat true 4 times, repeat false 12 times. And that allows me to just say the first 34 is the treatment group, where 10 out of 34 yawn, okay? And then the last 16 will be the control group, where 4 out of 16 yawn, okay? And so because it's a logical vector and R coerces the true falses to zeros and ones, I can just take the mean of the treatment, or mean of this vector, and it's going to give me a proportion, okay? So I've got 10 trues, 24 falses, and if I take the mean, the trues become ones, and I get a proportion of 29%. For the control, I get 25%, and I can take the difference, and my observed difference is around 0.044, okay? So this is just inputting the data, okay? And then I'm going to use the function sample. In sample, we'll just shuffle the order of these 50 true false values, okay? So I run sample and it just mixes them up, and then I'm gonna just take 34, throw them into group A, and then 16 into group B. And so that's what I do on this thing, right? So I take that vector of 50, I do sample, and that just shuffles the order. And then I say the first 34 goes into group A, the last 16 goes into group B. So here I know who ends up in group A and who ends up in group B. Has nothing to do with anything other than the random process, right? Because that's all that's going on, is we just randomly shuffled them. We put some into group A, some into group B, okay? And I just say, okay, what is the proportion of trues or proportion of yawners in group A? Okay, coincidentally, I also get 29.4%, 0.294. What's the proportion that ended up in group B? And coincidentally, I get 0.25. I get coincidentally the exact same values that came in the Mythbusters thing, okay? So this, what we observed in Mythbusters, this difference of 0.044, that just happened by coincidence on my very first randomization trial, okay? But we're not going to just do this once. We're going to do this many, many, many times, right? So if I do it again, I do set seed. I just, again, shuffle who's yawning, okay? Shuffle that vector of 50, put 34 into group A, 16 into group B, okay? And in this case, 23% of group A yawned and 37 in group B yawned, okay? So here I get a difference of negative 14% basically, okay? But this is what we're gonna do. We're gonna do this thousands of times. Does this make sense as far as what we're doing? We're just randomizing the assignments ourselves, and we're just gonna see what could happen, okay? Because here in this case, we know that randomization is the only source of the variation here, okay? So I just say, let's do this 10,000 times, okay? And then I just run a for loop over all 10,000 things. Each time I just shuffle this using sample, 34 into group A, the last 16 into group B, and then I take the difference between the proportions by using mean, okay? Which is a really nice thing about R, is that you can just coerce the logical vectors into proportion by using mean, because it'll coerce them into zeros and ones, and then the mean of zeros and ones is basically your proportion. Okay, and so what do we see? The average, the mean, indeed is around 0.00198, which is what we would expect. Okay, and the median is what we observed, this difference of 0.044. Okay, and so our empirical p-value is what is the probability of getting our observed difference or something more extreme if the null hypothesis were true. Okay, and so we observed a difference of 0.0441175, and the question is, what's the probability that the randomness produces a difference of 0.044 or something more, right? Our alternative is that the proportion in the seed group is greater than the proportion in the control group, so we're only interested in a difference of positive 0.044 or something larger, right? So this is what I do, and so I take. So this here is a logical vector. Differences is values like 0.04 and 0.13 and whatever. And then the observed difference is this value of 0.044. And I'm saying, are the differences greater than or equal to the observed difference? This quantity inside here is going to be a logical vector of trues and falses, 10,000 of them. And then I'm asking for the mean. So what proportion of these differences are greater than this? And it says around 50%, 51%. Okay, so my p-value is really big at 50%. So my empirical p-value after 10,000 of these randomizations, around 5,000 of them, over 5,000 of them, produced a difference of 0.044. Right. So this basically means the randomization process has a high probability of producing the data we observed in the Mythbusters experiment. Okay, so we have no reason to believe that the data we observed, that difference of 0.044, was caused by something other than randomness. Right. So all we've shown is that randomization could produce this difference of 0.044 very easily. Okay, so we would not reject the null hypothesis. The data does not provide reason to believe that getting a seed yawn makes a person more likely to yawn. All right. So we say we do not reject the null hypothesis, all right? And I hope your intro stats class went over this, but you can say do not reject the null, but you would never say we accept the null or we prove the null, right? Okay, so we cannot say that yawning is for sure not contagious, okay? We can't say that, right? Our data simply does not provide evidence that it is contagious, okay? So evidence, not having evidence that it is contagious is not saying the same thing that it's not contagious, right? So there's a few possibilities, right? It's possible that the seed yawn actually increases the probability of a yawn, okay? And it's just that we don't have enough data to show this, right? Maybe it increases it by only like 2%, and you need a lot of data to detect that kind of difference, okay? So that's a possibility, right? Another possibility is that it does increase, and that just for whatever reason, we happen to get weird data where it looks like it doesn't make a difference, right? So that's a possibility, right? Because of randomness, it's possible that we got something different, right? And then the other possibility is that it doesn't increase the probability at all, and the data we observe is completely normal or within expectation. So who knows, right? This is not what we had, but if we had a two-sided alternative, maybe our alternative hypothesis had a question something like, does seeing someone yawn have any effect, positive or negative, on a person yawning, right? And in that case, we would have a two-sided alternative, right? We would be interested if the difference is 0.044 or something more positive, or negative 0.044 or something more negative. So in that case, we would put an absolute value around the differences that we observed, okay? And so here we would do mean of the absolute value of differences greater than or equal to our observed difference. And in that case, we get 1. Our p-value is 1, right? And that feels like, is that for real? Can you get a p-value of 1? Okay? And you can for discrete cases, all right? And so let me just kind of show you, right? So in our case, we had 10 out of 34. Our difference of 0.044 came because 10 out of 34 in the seed group versus 4 out of 16 in the control group gives us a difference of 0.044, okay? Now, if another person, right, if the assignment ended up different, I would have 11 in one and 3 in the other group, right? Because if we're saying 14 people are destined to yawn, okay, I could split it up 10-4 or 11-3, and I would get a difference of 0.136, okay? If I went the other way, and I said 9 out of 34 and 5 out of 16, okay? If I split my 14 people that way, I would get a difference of negative 0.0477, and if I take that even further to 8 out of 34 and 6 out of 16, I would get negative 0.139, okay? So as far as the differences that are possible, I'm either going to get positive 0.044, positive 0.136, or something even bigger, or negative 0.047, or negative 0.139, okay? It is, even though my null hypothesis says we're expecting a difference of 0 between the proportions, it is physically impossible to get a difference of 0 because we have a whole number of people in each group, right? You're either going to have 10 and 4 in this group or 9 and 5 in the group, okay? You can't end up with something like 9.5 and 5.5 because you have a whole number of people. And so you're either going to get a difference of 0.044 or negative 0.047, and you know all of those are greater than or equal, the absolute values are all greater than or equal to 0.044. So it's not possible to get a proportion difference smaller than 4%, okay? So anyway, so it is possible in this case to get a p-value of 1, which is, in general, we would say that seems strange to get a p-value of 1, but in this case, that's exactly what happened, okay? So all to say is that this difference of 4% that we observed on Mythbusters could very well have been the result of random chance, okay? And we would not say provides evidence that yawning is contagious. Okay, anyway, exchangeability happens only with random assignment of treatments, so only do a randomization test if your data comes from some kind of experiment with random assignment, okay? We'll take a look at the other scenario, and that's going to be the bootstrap test, and that'll be on Wednesday, so we'll see you guys then.